Thank you. Hello everyone, I am Chao. Now I'm the chair of student chapter. Today it is my great pleasure to welcome you all to today's seminar. We are very excited to have Chao Wang with us to share her research. She is a great researcher in the computational engineering. Now she is a PhD candidate in civil engineering at the University of Illinois Urbana-Champaign after she earned her master's degree in civil engineering with honors from Tongji University. Her research brings together computational mechanics, multi-material, and multi-physics topology optimization, as well as additive manufacturing to design and fabricate intelligent material systems. Her work spans a wide range of interdisciplinary applications, including soft robotics, adaptive infrastructures, and biomedical engineering. Chao's work has been published in those top journals such as Advanced Science, Additive Manufacturing, and Computer Method in Applied Mechanics and Engineering. She has also been recognized with several prestigious awards. Now please join me in welcome Chao Wang. I will mute myself. Now
Thank
you
you,
can share your
Yanrong.
screen.
Yeah,
Thank you.
thanks for the introduction. And hello, everyone. So let me share my screen first. Good morning, everyone. So I'm very honored to have this opportunity to give a talk about my research. So my PhD work is mainly focusing on the magneto-active soft material. So in this work, we are trying to establish a computational framework, including the inverse design, advanced manufacturing, and looking for the potential applications of this type of material. So to begin with, I like to start with the introduction of the magneto-active soft material. And so here we focus on the hard magnetic soft material. And this material, it's essentially a two-phase composite, including the soft elastic matrix and the rigid hard magnetic particles. And the property of this material is that, so after magnetizing, those magnetic particles can retain a high remnant magnetization. So for example, as shown in this figure, so those remnant magnetization enter the magnetic field. So these magnetic particles tend to align with the external magnetic field. So this magnetic torque will drive the structure to deform. So some advantages, first, it can have a very fast and reversible large deformation. And also we can apply the magnetic field wirelessly. And lastly, the magnetization can allow us to design its distribution so that we can manipulate with the mechanical response. So, and because of those advantages, there are many interesting applications using this material. For example, as shown here, they designed some robot moving in a stomach model. And in this work, they designed this robotic bar so it can navigate inside the circular network to do some interesting tasks. And this work, they designed some metamaterial for the wave control application. So based on that, my research work is to investigating a framework integrating the design and the advanced manufacturing method to fabricate those designs. And finally, we are also investigating the potential applications using this fabricated design. So in the next of this talk, I will introduce them one by one. So first, let's start with the modeling and design part. So in terms of the modeling of this hard magnetic soft material, we adopted this simplified model published in GMPS in 2019. So this model describe the Helmholtz free energy function into two parts. The first part is the hyperelastic stored energy function to describe the nonlinear elastic property. And the second part is the magnetic free energy. So there are some key assumptions of this model is that it assumes the material retain a high remnant after magnetizing. And in the undeformed configuration, it assumes the magnetic flux density varies linearly with applied field. And lastly, the applied magnetic field is assumed to be uniform. So using this model, it allows us to deal with the high computational expensive topology optimization. And in terms of the first part, the hyperelastic energy function, so I like to point out that in the original model, they assume the material is homogeneous. However, the material is essentially a two-phase material, including the rigid particle and the soft elastomer. So to addressing this assumption, in our recent published work, we adopt an analytical homogenization-based model originally developed for the field elastomers, and we are investigating its application in the hard magnetic soft materials. So basically, in this material, it describes the energy function with respect to the volume fraction of the particles. And so here, the stored energy function can be an incompressible elastomers, and the material constants are characterized from the pure soft matrix material. So it explicitly considers the contribution of both the matrix and particles. So the key advantage of this model is that we can just use one-time characterization of the matrix material. It can allow us to predict the mechanical response of the magnetic materials at any field volume fractions. So based on this model, we also did a series of experimental validation to validate if it can work well on the hard magnetic soft material. So this page shows the uniaxial tension and compression test. So we focus on different matrix materials, and within each group, we also consider different volume fractions. And again, so within each group, we just need to characterize one of the 0% material. And then for the other cases, we just plug into the volume fraction. We can quickly predict its mechanical response. So this comparison shows the validity of this model. And then, so based on this model combining with the previously introduced magnetic potential energy, so we use it for the inverse design of the hard magnetic soft material. So here we consider different functionalities. For example, we can inverse design the metal surface to achieve different shapes, or design a robot have different locomotions, or the actuators to have different actuation modes. So to achieve that, we mainly use the topology optimization method, so which is to find the material distribution within a prescribed design domain, and it is to minimize a certain objective function under a set of constraints. So using the topology optimization for this problem, we need to think about how to describe the design, how to parameterize the design. So in this context, we use three sets of physical variables to represent the design. The first one is the density. So basically, we use the density variable to represent if there is material or not. And the second one is the magnetization distribution. So we prescribe a set of candidate magnetization directions, and we can optimize the direction of the magnetization at some location of the design. And lastly, we can also program the applied magnetic field, which is the external actuation. So with these three sets of design variables, it will form our final design and its corresponding response. And in terms of the optimization formulation, so we mainly focus on the displacement-based objective. So, for example, we can set set of target displacement at a certain region of the design domain, and we can also extend the program to the entire force displacement response. And the constraints we can consider the constraint like the volume constraint, stress constraint, and the box constraint for those design variables. And so with this design framework, so in the next I'll show some interesting designs we obtained. So the first one is the Kirigami Magneto-Active metal surface design. So in this example, we prescribe this design domain, so which is very thin sheet design domain and has some spiral cuts for the Kirigami. And then in this case, we optimize the magnetization distribution under a prescribed magnetic field. And we set a series of target deformations for different cases. And here is the corresponding optimized design. And here is the numerical result under our magnetic actuation. So we can see it can fit the target shape quite well with a very minimal error. And in this example, we use this framework to design a spider-shaped robot. So here we specify this spider-shaped domain, and we set the target shape to be some biomimic motions like the walking and climbing. And here we optimize the magnetization distribution as well as the external actuation, the magnetic field. And finally, this is our optimized design. And using this one design and this corresponding magnetic field, we can see the numerical result can be actuated as the targeting result target response we prescribed. So now, after we having this optimized design, the question is how we can fabricate them. So in the next, I will introduce the manufacturing method we have investigated. So I will specifically focusing on two methods. The first one is the mold casting and assembling method, and the second one is the direct ink writing method. So the first one, in terms of the mold casting and assembling, is very straightforward approach. So given this optimized design, so we will first prepare the material ingredients. So here we mix the materials, the matrix and the magnetic particles together, and then we 3D print the mold and according to the geometry of the design. And then we can pour the materials into this mold. And I like to mention that in this stage, those embedded magnetic particles are, those dipoles are randomly oriented. And then after curing at a high temperature, the material becomes solid, and then we take the material out and we magnetize it using a very large impulse magnetic field to align those embedded particles into the target direction according to our optimized design. And after this magnetizing, we can use another mode and put those magnetized members in and bond different parts. And this will form our final fabricated samples. So this method is quite robust and straightforward. It can be used quite well for fabricating the designs with those discrete magnetizations. And so I'll show some example that we fabricate using this method. So here is the spider robot that I previously introduced. So this one is what we fabricated using this mold casting method. And we actuated by applying the magnetic field. And we can see the experimental demonstration agrees well with the numerical result. And another method for the fabrication is the direct ink writing method. So the direct ink writing is a method that it can enable the magnetization aligned with the printing path. It's developed originally in 2018. So first, let me introduce what is the mechanism of the direct ink writing of the hard magnetic soft material. So basically, we will prepare the ink first, and then it will extrude the ink out under the pressure, and so it will form the structure layer by layer. And some key characteristics of the DIW is that, so for the magnetic material, the ink is composed of the magnetized hard magnetic particles and the elastomer matrix material. So originally, because it's in the liquid state, so the dipoles are randomly oriented. And then we attach a small magnet next to the printing tip, and that magnet will generate a magnetic field at the tip. And when the particles pass through this region, so this magnetic field will drive the particles to rotate and align it with the same direction. And then when the particles drop off on the printing bed, the direction will align with the printing direction. So here shows one demonstration of the printed sample with the magnetization pointing toward the left. And after printing, we can actuate this sample so it can have the magnetically actuated deformation. So by using the DIW technique, we can observe that we don't need to post bond different members like what we did in the mold casting method. And it also enables the continuously varied magnetization. So based on this method, to adapt our design with direct ink writing, we adopt the following strategies. So firstly, we extend our topology optimization for the continuous magnetization distribution. So the magnetization in this case can vary in any directions. And secondly, we also need to deal with the path generation, how we can generate the tool path with our optimized magnetization direction. And finally, we fabricate those optimized design using the direct ink writing and also did a series of experimental validation. So first, in the first part about the topology optimization, so here we extended to consider some DIW requirements. So compared with our previous work, we prescribe a certain number of magnetization direction. And in this case, we specify the magnetization direction to be oriented in any arbitrary directions. And also, the magnetization magnitude should be uniform because we cannot change the magnitude during the printing. And lastly, we also would like to have the structural members to have sufficiently large and well-defined members. And also for the magnetization direction, we would like to make it smoothly transit so that will make the printing smoothly. So by incorporating those into our topology optimization framework, so we can have the design with those variously changed magnetization. And based on the optimized design, we move forward to the second purpose to align our printing path with optimized magnetization direction, and at the same time, it should preserve the optimized geometry. So to solve this problem, we use this global parameterization. So basically, we define this orientation energy, and we try to find a scalar field that making its contour line align with the direction of the target magnetization. And after doing that, we can just use the contour lines as our printing path. So to do that, given this optimized design and the corresponding magnetization, we first rotate the magnetization vectors by 90 degrees, and then we solve this scalar field by making that its gradient aligning with this rotate magnetization direction. So after having this scalar field, we can extract its contour lines as our printing path. So that's what we did in the next step. So we extract the contour lines coordinates, and this will also introduce some redundant regions. And we can further remove those redundant contour line region. And also, because the contour line, it can be bidirectional, but the magnetization is just has one unique direction. So we also need to identify the target direction. So here we compare the cosine similarity, and we adjust the sequence of the coordinates of the line segments to make it aligning with the targeted magnetization. So finally, we can also have different post-processing procedures. For example, we can remove the toolpath that have extremely short length, and we can also adjust the resolution to make it compatible, to make it efficient for the storage. And we can also sort the printing sequence of those lines. In this case, we prefer the next lines printing next to the last printed filament. And also we can, in the end, we can convert those line coordinates to the printing format compatible with the printer. So after having the design and the printing path, I'd like to introduce some examples we have achieved. So the first one is a Magneto-Active elevator. So in this case, we are trying to design the geometry and the magnetization to lift this central part. So here is our optimized design, and those colors representing the magnetization direction. So it varies continuously. And this shows our solved scalar field, and its contour lines align with the optimized magnetization direction. And using this printing path, we start with direct ink writing, and this shows one of our printing process. And after curing the material, we also did the experimental validation. So this shows the deformed state. We apply the magnetic field, so we can see it can lift this central part as designed. And the second example is another butterfly-shaped metal surface. So in this example, we use this very complex design domain. So it has many inner holes. And in this case, we try to optimize the magnetization orientation to make it can achieve different shapes. For example, the flying, alternating, and warping shape. And in this case, we use this half-domain design, and the purpose is mainly to reduce the time cost in the topology optimization. And finally, we got this optimized design for each case and its corresponding generated printing path. So we can see those printing path indeed varies continuously. And based on that, I like to show a close comparison with the printed sample and our printing path. So we can see those printed filament, actually it can be printed quite well and following our generated printing path. So in this case, because we designed them use one symmetric half, and to get the entire structure, we print them one by one and then bond them together. But I like to point out that we can also print them, design them as a whole structure, and then we can also print them as the entire structure. So using this butterfly design, we also did experiment validation, and this is a photo showing our printed sample, and we apply the magnetic field. And this shows a comparison of our numerical design and our experimental design. So it can be seen the deformed shape matches quite well with our numerical prediction. So in this example, we show that we can use the same design domain, but by slicing the same topology into distinct printing path, we can make it to have different morphed shapes. And I like to play the video for this experimental validation. So the magnetic actuation, we generated the magnetic field using the Helmholtz coil. So we can see the deformation is quite fast and is reversible. And the last example is about a metamaterial design. So in this case, we are trying to design a metamaterial. The objective is to have the area shrinking. And in this case, we use a unit cell design with the periodic boundary condition. And this is what we obtained using the topologization. And this shows the deformed shape of this unit cell under the magnetic actuation. And then we can assemble the structure and use the assembled structure to generate the printing path at one shot. And so as we can observe, so between different unit cells, those printing paths can transit very smoothly, and it can be generated very efficiently. So with this assembled structure printing path, we can did the experiment. So this shows the comparison with our numerical result. The undeformed state, and under the actuation, it will deform to achieve the area reduction. And here is a video showing the actuation process. So then that will conclude the story of our manufacturing strategies. So basically, we have two different approaches. The mode casting is suitable for the discrete magnetization design, and the direct ink writing approach enables the continuous magnetization design. And lastly, so based on the fabricated design, we are trying to see where we can apply those designs for the real-world application. So in my recent work, we are mainly focusing on the topic of the mechanotherapy. So basically, we are using the generated design to implant to the tissue for the mechanotherapy purpose. So first, I like to introduce the mechanotherapy background. So the mechanotherapy, which is to apply the mechanical force to injured tissues. And some recent studies showing that by applying this mechanical force, it can promote the tissue recovery and regeneration. But some limitations in the current method is that the mechanotherapy device, so typically it's very hard to reach the deep tissue. And also it cannot control the exact tissue deformation. And lastly, for example, in this work, they developed this implantable robot. And by implantation, it has to be connected to some wire for the actuation. But for the Magneto-Active soft robot, because the magnetic field can be applied remotely, so that enables the wireless actuation. So in our work, we are focusing on using the designs to generate the wirelessly controlled tissue deformation for the mechanotherapy purpose. So basically, we can implant this robot to the deep tissue, and we apply the magnetic field externally. So it doesn't have to be connected to any wires. And also it's effective for deep tissue by implantation. And because we can also use the topology optimization framework to inverse design the robot to achieve different target tissue deformations. So that makes our design, the tissue deformation, programmable and controllable. So in this study, in the topology optimization, we basically will consider the modeling of both the tissue and the robot. So as shown here, this gray region represent the robot design region, and this red region represent the design of the underneath tissue. So this video shows the optimization process. So basically, we can specify a target tissue deformation, and then we can optimize the robot geometry as well as the magnetization distribution. So to achieve this target tissue deformation. And by modeling the tissue and the robot, as well as their interaction, we can get our optimized design as shown here. And so in the next, I will show some examples that we achieved using this hierarchical modeling and topology optimization. So here in this case, we specify a bioaxial motion of the tissue, and we are trying to use one design to achieve bioaxial stretching or the bioaxial compressing in the tissue. And this is what we achieved for the robot. And it's the experimental demonstration and also the FEA result. And the second case is different target tissue motion. So here we define this uniaxial motion that is to expand in one direction and compress in another direction. And this is a corresponding numerical and experimental validation. And the third case is that we are designing the shearing motion of the underneath tissue. And this was the optimization framework generated. So it under the magnetic actuation, it will rotate clockwise. So it will generating the underneath tissue to shear at opposite direction. And lastly, we have this dual mode motion design. So that is, we want to use one design to have two different motions. One is this stretching motion to cause the stretch of the tissue, and another is the shearing motion. So basically, we're combining these two motions into this one design. So this is what we have obtained. And so based on those optimized design, we firstly did the ex vivo validation. And in this work, we used the porcine skeletal muscle tissue. So the process is that we bound the robot to the surface of the tissue, and then we can also spray the speckle pattern for the DIC analysis so that we can quantify the displacement of the tissue. And this demonstration showing that the robot movement can indeed generating the underneath tissues movement. And so finally, a quick conclusion for this work. So after finishing this ex vivo experiment, we showed that we can control the tissue deformation in the macro scale. So for example, here, by playing with the external magnetic field, we can manipulate the tissue displacement. And also it is sustainable under the cyclic loading as shown in this figure. So it can sustainably generate a sufficient displacement of the tissue after the cyclic testing. And also we can use the DIC to quantify the displacement field. So as shown in this figure, we can quantify the underneath tissue displacement. So the displacement field reveals the different motions can be achieved successfully. And we can further compare our experimental result with a numerical result, which also shows a close agreement. And in this work, we are also currently working on the in vivo validation by implanting the robot to the mice model. So we apply the actuation externally, and we will analyze the muscle force to see if it will indeed have this mechanotherapy effect. So that will conclude my talk today. So basically, my work is mainly working on the framework for the Magneto-Active soft material. So for the modeling part, we integrate a framework for the rapid prediction of the nonlinear elastic response of magneto-active materials and supported by a systematic experimental validation. And in terms of the design, we developed a topology optimization framework for the optimization of the density discrete magnetization distribution, as well as the external actuation magnetic field to achieve the three-dimension displacement control. And for the manufacturing, we use different approaches to fabricate our optimized design, the mode casting method and the direct ink writing method, together with the path generation algorithm. And finally, we also investigate a biomedical application of this optimized robot for the controlled tissue motion, and with our in vivo validation currently ongoing. So here are a summary of the related publications for this talk, and all the work has been completed within the mission lab in the UIUC. And also I acknowledge the financial support from the DARPA and the NSF agency. And thank you everyone for your listening, and I'd like to take any questions if you have.
Hi, Charles. Thank you so much for your impactful research. Does anyone
Thank
has
you.
any questions?
Hi, Chao. This is
Hi.
Shenhu. Yeah, very great presentation, very fascinating topic. I have one question about the direct ink printing, that technique, because you change the material from liquid to solid. So do you expect any, I don't know, viscous properties in your material, or do you think it's just pure elastic?
Yeah, that's a good question. So actually, for the direct ink writing part, the material during the printing, because it's still the liquid, so the viscoelastic property is a critical factor that we need to consider during the printing. And so to do that, we also characterize the viscoelastic property of the material ink. But after printing, so we cure the material to be solid. So in the solid state, once we apply the magnetic field, it can still deform hyperelastically. So in this study, during the actuation, we didn't consider the viscoelastic property, but it would be critical to consider during the printing stage. Does that answer your question, Shen?
Oh, yes, thank you.
Yeah, thank you.
I also have a follow-up questions.
Mhm.
Well, in your equations used for the hyperelastic free energies, do
Mhm.
you think there is no deformation with those magnetic particles?
I see. Yeah, that's another good question. So basically in this model, we are using it's a stretch-based model. So the particles, so we neglect the rotate. So basically, it's stretch-based particle, and we are assuming the particle to be rigid. But for the more accurate modeling, we should also consider the rotating of those particles. And there are also some advanced modeling and the full coupled modeling developed for this full coupled problem. And here we use this simplified model is mainly for the reducing the computational cost in the topology optimization.
I see. Thank you.
Can I ask a question?
Yeah, sure.
Thank you for your fantastic talk. I have two quick questions. So the first one is about like your experiment, your DIW 3D printing experiments. It's like were you guys able to visualize whether or not those rigid magnetic particles are really aligned along the printing path, 100% aligned or 90% aligned or something? Were you guys able to quantify how much alignment that it was after printing?
Yeah.
And
Yeah, thank you.
sorry, the second question is about your optimization scheme.
Mm.
Like would you mind like elaborating a little bit more about how you guys were able to do the optimization considering this is target optimized design, and how you guys were able to achieve that target optimized design? How was the computational cost? Thank you.
I see. Yeah, thank you so much for the questions. So regarding your first question, yeah, that's a very important point. So a straightforward way to visualize the particle alignment. So we are also trying to see if we can use some microscopic image to visualize the particle alignment. But as shown in my previous figure, although this is not used for the DIW, the particles are the shape is quite randomly, and it's very hard to visualize if it's aligned or not. So to quantify the alignment, what we did is that we compare the remnant magnetization. Not sure if I have that in the backup slides. Yeah, I didn't include it in the backup slides here, but basically, so we can measure the magnetic flux density of the printing samples. So for example, showing this figure, if for a fully magnetized sample, we magnetize the solid and we measure the magnetic flux density. So by doing that, we have an ideal value. So basically the maximum magnetic flux density we can achieve without DIW. And then we use our DIW to print a filament and cure that filament, and then we measure the magnetic flux density of that printed filament. So by comparing these two values, we can somehow quantify the reduction or the alignment during the DIW. So based on our measurement, it's found out that by using the DIW, the generated magnetic flux density will be around 60% compared with the maximum value. So that's to some extent can reflect if the particles are aligned or not.
Thank you.
Yeah.
So it's like based on that, it's like your alignment is about 60%, roughly.
Yes.
Okay. Thank you.
And in terms of the topology optimization method, so for the optimization, the first part is about the design parameterization. So basically the design variables we are going to optimize. So in this case, we have the density, which representing the geometry, and the magnetization distribution, representing the magnetization direction. So we define this M design variable. So and this BR is just a vector to defining the direction of the magnetization. And then we also can parameterize the external magnetic field. It's also defined as a uniform vector. So by using these three design variables, we can interpolate our magnetomechanical model. So here we use this sim penalization method. And then we set this target displacement. It's reflected in the objective function. So for example, if we want to control the displacement at this point, we can try to minimize the error of the actual displacement and the target displacement. So that will be our objective function. We are minimizing the difference between the actual and the target displacement. And the constraint will be for example, the volume constraint, the percentage of material we are going to use, and also the stress constraint. We can avoid the thin members occurrence. And we also use the filtering to have the well-defined members, and also the heavy side to promote the discreteness of the design. And in each optimization iteration, we solve the nonlinear FEA problem. And so it will minimize the objective until converging. So that is the overall story of the topology optimization.
Thank you so much. That was very informative. Thank you. Fantastic talk.
Thank you.
Thank you, Chao. I also get another two questions. The first question is, in your optimizations, can you achieve the accurate optimize, like to control the height of the race of the butterfly wings, or like how much it could arise after the design?
I see. Yeah. Thank you for the question. So in this design, for this butterfly shape, actually we use the maximization. So basically we maximizing the displacement at some points. So the objective function is maximizing the displacement at those regions. So basically the result, what we have achieved is one optimum solution. that trying to maximizing the displacement. But it's also very limited because here we didn't enable the optimization of the density. So if we also enable the optimization of the density, it will further increase the achievable displacement. But we can also use a fitting type. For example, we prescribe the displacement we want to achieve. That is also another objective we can have.
I see. Thank you. And I got another question. Because all those magnetizations may along different directions, so could this material maintain those magnetizations permanently?
Yeah, that's a good question. So based on our experience and also some studies from the literature, the magnetization can indeed decay as time going by, but it's a very slow decaying and basically the decaying is quite negligible compared to the fresh value after the magnetizing. And so for all those studies, we typically did experiment after the fabrication within month. So after a month, it can still have a very large deformation.
I see. Thank you so much. And we also prepare some general questions to ask us how. But for all those audience, feel free to break me if you have any question you want to also ask. And as I know you are a current student at UIUC, how do you like the graduate life, and what do you think to make you feel unique about it?
I see. Yeah, I think the graduate life in UIUC is quite exciting and challenging and but also very rewarding. So I'm in the department of CEE, and there are many world-class scholars, and I'm very honored to be get interacted with those professors. And the course provided in our department is also very helpful. And I learned quite a lot of knowledge that can be directly transferred to my research. And also I can get the opportunity to get exposed to some innovative courses that related to those professors' research, so which is very eye-opening and really helpful for my future research. And also we have many useful infrastructures and facilities, and it's very easy to initiate interdisciplinary collaboration. So I also work very actively with people from the biofield, and it's very inspiring experience.
Oh, that sounds great. Does the department very large at the UIUC?
Yeah,
Oh, that's nice.
we have Granger Engineering. It has different engineering departments, and we can also take the course from the other departments. So those experience really values.
Yeah, so can you take the computer science course freely without
Yes,
any?
yeah, we can register for it, but it's very popular. So sometimes we need to seize the option, occupy the class.
Yeah, that is always popular.
Yeah.
And, yes, and you are very soon for graduations. Do you have any advice for the current or those aspiring graduate students in the computational mechanics?
Yeah, I think for a computational mechanics student, mm, the first advice I would make is try to have a solid foundation of the computational mechanics. So the course we are taking is very important, and it will benefit us for a quite lifelong time. So get a solid mechanical foundation, such as the computational mechanics, solid mechanics, FEM, and the numerical methods. And secondly, be proficient in some numerical tools and try to master those tools to implement the mechanics to the simulations and designs. And lastly, I would say being open-minded to the interdisciplinary applications. So try to use the computational mechanics for some real-world applications. So try to be open-minded to see those possible opportunities for the real-world application.
Yes, thanks so much for your great advice. It's really helpful. And if you don't mind, we will upload this recording to our YouTube channels to help more people to have an understanding of those advanced research.
Yeah, sure, no problem.
Thank you so much. So, if no one has no further questions, we will end our today's seminar. Again, thank you so much for those attendings, and thanks for Chao for the great sharing.
Yeah, thank you, Yanrong, for the invitation. Yeah, nice to see you here.